Hello, welcome to this session about stellar spectra. We're going to consider how stars can be distinguished by analysing their spectra. So let's remind ourselves of how a spectra is created. So all light sources generally produce a continuous spectrum. So the emission of a thermal spectrum is one of a continuum across all wavelengths. Okay, so this would be a typical white light. Now, when we have just a hot gas, now what that happens is that hot gas produces very, very specific emission line spectra. So that's because the transformation between atomic levels gives out very specific wavelengths, and we therefore have emission line spectra. Now, if we have a very bright object and that is clouded by a gas of some sort, what happens is this gas will absorb certain lines of spectra, and that's related to the chemical composition of the gas itself. So therefore, by looking for those absorption lines, we can work out what is in the gas. Now this, thankfully, is what we see from a star, which has a very, very bright continuous source of light, but the gases around it give off very, very distinct absorption line spectra. So when we look at a star, and this is an example of a star, and the information we get, we'll see that it releases light in all wavelengths, like hot objects, and we've discovered that from Stefan Boltzmann's law anyway. And what happens is the star's atmosphere acts as this cooler blanket around the hotter interior, so therefore we see very specific absorption spectra. We also notice we see a change in intensity at different wavelengths, and we're going to think about that more in a moment. Now, if we look at lots of different stars, what we start to see is patterns emerging. So we can see at certain of these different stars, and they've got different names here. We've got O, B, A, F, G, K, and M. And we'll talk about that in a moment. That's actually the Havard emission spectra. What we do is that certain themes or certain lines seem to appear more readily for certain types of star and then disappear again. Now this list, this Havard emission spectra, what I'm showing here is actually a range of star temperatures. The Havard Spectra Sequence has a number of classes of star, O, B, A, F, G, K, and M. And what happens is certain strong lines are associated with certain classes. So we have ionized helium there, we have hydrogen, and those are the lines which we can identify from the absorption spectra of a star. Now, as it happens, I'll explain why this is in a moment, these different strong lines relate to certain classes of star which have certain surface temperatures. So as you can see, there's a range of surface temperatures there, going from O as the hottest and M down to the coolest. It also says colour of stars, and you may be perplexed a little bit by why stars have different colours. Now here you need to think about the fact that although they absorb or they emit, a star will emit at all wavelengths, certain wavelengths will have a greater intensity than others. Before I forget, a way to remember the order of the class of stars is this mnemonic, "Oh, be a fine girl, kiss me," and that's the order of the Havard Spectral Sequence. So back to what I was saying about colour and temperature. So due to the fact that a star acts a lot like a black body, what we see is that the peak of radiation is at a different wavelength. And dependent on the stars, what we observe in the visual spectrum is some colours dominating more than others. So here we have the hottest stars. Our sun itself has got that yellow colour to it, and the least luminous stars will have a red colour to it. and that's all dependent on the fact that that's where the peak intensity of light which we observe is seen. Now, if we think back or remember, this relationship has actually been mapped out. We go forward into something what's known as Wien's law. So Wien's law identified that the wavelength of maximum intensity is inversely proportional to the Kelvin temperature. With this relationship, once we know the constant, allows us to look at a star, find out what its maximum wavelength is, and then be able to deduce the temperature. As it happens, this constant is 2.898 times 10 to the minus 3. So we can use this fact if we look at the maximum wavelength or maximum intensity wavelength, then we can work out the temperature of the star. So it's another way of looking at a star closely across all wavelengths to be able to find out additional information. So there's two things to think about there. We've looked at the spectral lines and how they're associated with certain temperatures, and we can also look at the peak wavelength, the peak intensity wavelength, and that also tells us the temperature of the stars. So these two features allow us to better understand a star remotely without having to place a really long thermometer. So, past exam questions. Observations show that the sun is yellow-red, so therefore its maximum wavelength is about 500 nanometers. Use Wien's law to calculate its surface temperature. Second question. What is the dominant color emitted by a star at 20,000 Kelvin and at 5,000 Kelvin? Express your answers in wavelength. So both of these use Wien's law, but in both directions. Take a moment, use that calculation. And what you should find out is the temperature of our sun is about 5,796 Kelvin, about 6,000 Kelvin. And the wavelengths we see of a very hot star and a much cooler star, we see that the peak wavelength of a hot star is 1.5 times 10 to the minus 7, and a longer peak wavelength is found in a cooler star, and that's 5.8 times 10 to the minus 7 meters.